Recording in progress.
Yeah. चलो क्या था everyone? Just give me a minute. Great. So last thing that we did was this equipotential surfaces. The next thing is dipole. So what is this dipole? Chila, let's keep your cams on. So dipoles are simply, it's a equal and opposite charges with a small distance between them. And dipole is a combination of with a distance d between them. Now, if you think about this, actually, right, the dipole, technically in terms of physics, is not really a big deal. It is mostly an approximation. We encounter this thing a lot in chemistry. So this is how we take this. So minus q plus q. You must have seen in chemistry that dipole-dipole interactions. We have ever heard the word. So if you take the distance to be d, so we represent this with a p bar, which is given by charge, any one of the charge into the vector d bar. So this p bar is what we call as dipole moment. And d bar is a vector from negative charge to the positive charge. That's it. So the simple definition of dipole is this. Take two equal and opposite charges, keep them at a distance, and any one of the charge into the distance between them will give the dipole moment. It's a vector quantity. It is, the direction is given from negative to positive charge. Example, if you take an HCl molecule, We know the chlorine is more electronegative, so it will be slightly negative and this will be slightly positive. So this will be a dipole. So when you talk about hydrogen bonding, there also is nothing but a dipole, isn't it? So if you take something like CCl4, so here also if you look at this thing, this guy will become, let's say 4 delta plus, delta minus, delta minus, delta minus, and delta minus. So this will be this. So there we say then a dipole moment is 0. So suppose let's say if you have a system like this, let's say 2q minus q and minus q. So exactly not equal and opposite, but what you can do in this kind of a case, it's a 30 degrees and 30 degrees. I can split this into plus q and plus q, minus q and minus q. So you can basically split the plus 2q into two small pieces. This is one dipole moment and this is one dipole moment. Where p bar is equal to q into a, p bar is equal to q into a. And these angles are 30 and 30. So we can say the dipole moment of this system is 2 times p cos 30 j cap. So it just gives like a regular vector, you can add them and do everything. Check it out. Here you go. So using this thing, I'll give an example. You guys try to solve this. So let's say you have 4 charges here. Let's say this is plus q, minus 2q, plus 4q, and minus 3q. This is the square of side A. What's the dipole of this? Get the dipole moment of this system. Hmm. Let's see. So I can split this into plus q, minus q, minus q, 3q plus q, and minus 3q. So this guy will form one pair. This guy will form one pair. So this will be 3qa. This will be qa. This will form one pair here, qa. So dipole moment of the system will be 2qa I cap minus qa j cap. So for point charges, it is straightforward, right? You can just get the charges and finish it off. The only thing is you need to have equal and opposite charges. As long as the total sum is 0, you can adjust them however you want. Is that clear, everyone? Now, find for this thing then. What if you have a shape like this? We got a ring. Radius r, and let's say the right half is positively charged. Lambda. And the left side is negatively charged. Minus lambda. Find the dipole moment of the ring. You have to prove it, Rayan. You just can't say I will use it. Because what will happen, right? If you don't prove it every time, exam also will get confused like this. So ask yourself, when can I use this? Is that valid here? And then use it. Let's see. We'll talk about that. But try. How do we do this? You have to integrate. That is clear. How do we do this? Var square. It's a vector quantity. Hmm. See. So at an angle theta, just give me a minute, everyone. Hello. Hmm. Let's see. Yeah, they're saying today J mains results will be out. People are going mad. Let's see. So if you take a small piece here, this will be d theta. So this part here will be dq, which is lambda r d theta. So if I go back here, this guy will be minus dq. Getting it? So this forms a dipole. So this dipole is like this. Let's call it dp and making an angle theta. So dp is nothing but charge lambda r d theta into what's the distance between them, 2r. So this is a small dipole between these 2 points, right? But remember, whenever you integrate a vector, we resolve them into components. 2 lambda r square d theta cos theta I cap plus sin theta j cap. This will be the dipole moment for this small piece, and then you're done. You integrate this. What are the limits? You're starting from this will be theta 0. If you go up, it will be theta 90, and if you go down, theta will be minus 90. So we get dipole moment will be 2 lambda r square integral cos theta d theta I cap integral sin theta d theta j cap, and this will go from minus 90 to 90 and minus 90 to 90. So that would be 2 lambda r square. How much is this? That will be one thing you can clearly see here. The vertical components cancel out. Cos theta integral will be sin theta. That will be 2 I cap. And that will become 0 actually. We get 4 lambda r square I cap. This is how you integrate. Is that clear, everyone?
Sir,
Yeah.
sir, rather than choosing the DQ exactly opposite, could we like
Mm-hmm.
start 180 degrees and then go up by theta like this, like making it symmetrical across the y-axis, and try that?
You can do that. You'll get the same thing. Doesn't matter how you do, you should get the same thing.
Okay, like it gave the same
As
thing.
long as you take two equivalent opposite charges, you'll get you the same thing. Don't matter. You're trying to do like this, na?
Yes.
There you're changing the distance every instant. So yeah. Clear with this? That also works. Now, same thing. Suppose if they frame it like this, the why you need to know integration is because of this. What if they give you lambda is equal to lambda not sine theta? And just call it a b part. Now, how will the charges be? Remember, theta is taken from here. So sine theta is 0, so there'll be no charge. Then as sine increases, we'll have little charge, little more, little more, more, highest at the top. And then as you come down, it will decrease, 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 and 0 again. As you go down, you'll get negative, more negative, more negative, more negative. So even though it is non-uniform, there is still some kind of symmetry here. Find the dipole moment of the system. The idea is the same thing. The way you take element and everything. Arush, are you getting this? Yeah, let's focus on the class. Let's try. Adjust your camera a bit, na, Arush? I can't see you clearly. Kritik, adjust your cam. Parth, Vignajit. Please make sure your faces are completely visible on the screen. Let's try, everyone. Let's try. You have seen already this thing once. What I do. Same thing you have to do. बस lambda का place में lambda not sin theta will come. That is the only difference. Try. I'll give you a minute or two. Pi r square lambda. Any answers? 2i plus pi. No, Shana, that's not. Purvaja pi r square 8 lambda. No, in your answer you'll get a pi also. I think you guys are getting stuck with the integration part. Okay, let's see. I think we haven't got something. Same story here. Let's take a small piece here. D theta, so this guy will be 1. This guy will be your minus dq. This will be dq. The dipole moment dp bar will be lambda naught sine theta into rd theta. This is the charge. Into the distance between them is 2r. The vector will be cos theta I cap and sine theta j cap. So nothing changed. If you see, it's the exact same problem. The only difference lambda ka place mein you will put this thing. Lambda naught sine theta. So this guy will be 2 lambda naught r square. Now you will get cos theta sine theta I cap. Sine square theta d theta j cap. Integration limits will go from this point. Theta is 0. If you cover a semicircle, theta will be pi. So limits will go from 0 to pi. So be careful with the limits. So how do we integrate this? So let me show you this. So integral sine theta cos theta d theta 0 to pi. This can be written as half integral sine 2 theta, 2 sine theta cos theta. This guy will be half minus 1 by 2 cos 2 theta. Limits will go from 0 to pi. Cos 2 pi is 1, cos 0 is 1. This thing turns out to be 0. We can clearly see here the I cap cancels out. The component is only in the j direction. So integral sine square theta d theta 0 to pi. This can be written as 1 minus cos 2 theta by 2 into d theta. This thing also, if you integrate, that cos 2 theta will be sine 2 theta, you'll end up with actually pi by 2. There you are done. Substitute here. So we'll get 2 lambda naught r square. This I component is gone, and this will be pi by 2 j cap. So the answer is lambda naught pi r square j cap. Yeah, right, Rehan, you got it. Check this out. Clear, everyone. So this is how you integrate this stuff. Now there is one thing there. If the charge distribution is uniform, we have a trick, which was Anshu was saying it. Now look at this thing. When you said the dipole moment p bar is q into d bar. So if you have multiple dipoles, so pi q di, so p of the system will be sigma qi. So if there are multiple charges and multiple dipoles, qi di. Again, if you look at this thing, this kind of looks like our center of mass is sigma mi. It's a linear function. So you can write m into r center of mass sigma mi ri. So if you can actually find the center mass of a system, you can actually use this. So this will be useful, especially for uniform distributions. So when this was plus for a ring, there is a ring of center mass. You can put plus q here, and this distance will be 2 r by pi. You can put the minus q charge here, and again 2 r by pi. Then you can replace this simply with charge into q into the distance 4 r by pi. But charge q is nothing but lambda into length. Here length will be half of it, which is pi r. 4 r by pi. So pi goes off. There, this was the same answer we got. This will not work for 40b part because it will work. But do you know how to find the center of mass for a ring whose mass density is like this? If you can find that, then you can use that. You getting the problem? Then the question would be like, you need to find the center mass of this ring whose mass density is lambda naught sine theta. Find the center mass of this, replace the charge, you will get the answer. Now the problem for this is you have to integrate. If you're integrating to find center of mass, why don't you just do the regular integration, isn't it? So normally for shapes whose center mass you already know, this is safer. This is for a ring. This thing especially becomes very important, when you have shapes like this. A ring to फिर भी you can integrate. If you take a disk or a solid hemisphere, integration would be a mess. But you can't take limits. How will you take limits? The plus is starting from here and ending from here. And theta is going from here. So if you take minus 90 to plus 90, you're taking from here to here.
Oh, sir, but
All the positive charges from 0 to pi record. You're taking this positive and this negative, right? Positive charges are starting from where and ending where?
right.
That way.
Yes.
They're starting at 0 and ending at pi. Na? Previous question, charges started at minus pi by 2 and ended at pi by 2. That way. So if this was a disk, where is the center of mass? Anyone remember? 4r by 3 pi. So dipole moment of this guy will be q into 4r by 3 pi into 2 times. So there you can keep doing this if it is a solid hemisphere. So quite a useful thing, if you have a non-uniform charge distribution, I can treat it like the regular center of mass thing and finish it off. If you give me non-uniform, then either I should know the center of mass, for which you have to integrate. And if you're going to integrate, better you just find the dipole moment with integration. So here the dipole moment will be q into 3r by 8 2 times. Is this clear, everyone? For uniform distributions, your life will become easy. You can just put it there and finish it off with center of mass. So always, before using the concept of center mass, ask yourself, is the function linear? Here in this case, it is linear. It is charged into d power 1, which looks like mi mass into r power 1. Mathematically, they look same. Any doubts on this? Clear, Nanj? Any doubts on this? Great. So this is the first part of the dipole, like, how to find a dipole moment of a system. The second thing, the field and the potential due to a dipole. So I'll tell you, see, what we are trying to achieve, like going like this. End of the day in chemistry, if you see, right, you're interested in what? Dipole-dipole interactions. So end of the dipole, what you're trying to find is if you keep two dipoles, how do they interact with each other? That's the kind of thing which we are trying to find. So first we define what is a dipole and we calculate a dipole moment. Second thing, we'll find the field and potential due to one single dipole, and we will take it from there. So if you have a dipole moment P bar, so this is plus q, this is minus q, and let the distance between them be d. So from the center, we are trying to find a field at some point here, A. And let this distance be r, and r is much, much greater than d. So we can find that, we will try to find the field and potential for points which are very far from the dipole. So r bar is a vector from dipole. You can say from center of a dipole. To point A. And we define theta is this angle. Now this is important. What is theta exactly? Theta is the angle between P bar and R bar. You can remember like this. Theta always goes from positive to negative angle. So if this is a dipole moment Q into D, if this is point A, theta is taken this way. Theta goes from plus Q to minus Q. ठीक है? Let's see how to calculate this. Logically speaking, if you just want to calculate using the normal method, what we do? We find this distance, and then we just use the field and potential and finish it off. The headache with this thing is finding this length is little difficult, and the directions are also not that great. So things get a little messed up. So we use some kind of an approximation. Let me call this point P only. So listen to this approximation which you're doing. This is important. This will again come in wave optics. So if you have the charge plus Q minus Q from the center, this is point P. Let's call this point A and let's call this point B. So I'm interested in finding A to P and B to P ka distance. Right, everyone? We want to find distance from A to P. We want to find distance from B to P. Right, Arush? Yeah. So see, look at the idea. This is what we're trying to do. So from point A, drop a perpendicular onto this point, and let's call this point A dash. From point B, drop a perpendicular onto this line, and let's call it B dash. This angle will be theta. This distance will be d by 2. Let me exaggerate this. So this was the line A and B. This was theta. This is what you're trying to do. From here, you're dropping a perpendicular. This guy was d by 2. This length will be d by 2 cos theta. Drop a perpendicular. This length will be d by 2 cos theta. This is A dash and this is B dash. So this piece of length which you get here is d by 2 cos theta, and this is also d by 2 cos theta. So this is the approximation which we use. We say AP is almost equal to A dash P, right? Which is R minus d by 2 cos theta. BP is almost equal to B dash P, which is R plus d by 2 cos theta, the additional distance. Now, let's see why this works actually. The thing is, all this works only because R is much, much greater than that small d. See, when we say R is much, much greater, this is what we're talking about. This is the dipole moment. You're getting how far is this point? You're talking about such a small dipole. The dipole ka length is in millimeters, and this distance is something like maybe 1 meter or something. And now we are saying this length, which I want to find, and if you drop a perpendicular, and this length are almost equal. You're getting? The distances are quite large, meaning in this picture, it looks like, you know, this dipole is big. I drew it that way, but actually the picture looks something like this. The dipole is so small, it's almost negligible, something like this, and we're talking about this point here. Is this making sense, everyone? So that approximation is kind of valid. So that one approximation, right, saves us a lot of calculations. But please have a look at these approximations. Quite important. You will again notice the same thing in wave optics. I will teach you then when it comes. But this is the idea there. So instead of finding from A to P, we are trying to find A dash P. Instead of finding B to P, we are finding B dash P. Is this approximation clear, everyone? Clear? And then once we got this is what we do. So we have our dipole. Point A, theta, R. This is A and this is B. This is plus Q and this is minus Q. So the potential at point P will be, due to this plus charge, it will be KQ by AP. Due to negative charge, it will be KQ by BP. Since AP is almost equal to B dash A dash P, R minus D by 2 cos theta, I can substitute this. KQ by R minus D by 2 cos theta minus KQ by R plus D cos theta. Cross multiply. You will get KQ by, denominator will be R square minus D square by 4 cos square theta, and the numerator there becomes 2 D by 2 cos theta, you'll get D cos theta. But what is Q into D? P. So this will be Kp cos theta by R square. Since R is much, much greater than D, we can neglect this. And we know P is nothing but Q into D. Check. That's your formula, everyone. So the potential due to a dipole at a point P is given by Kp cos theta by r square. I'll write this in the next page in a more usable form. You can write it down. Then how do you find the field? Now remember, I taught you the field is dv by dr, but that is only in one direction. If you actually see in polar coordinates, the differentiation looks something like this: dou v by dou r er cap. This is not important. We don't have in the portion, but just have an idea. R d theta e theta cap. There's also third one also, e phi cap. That is okay. So er cap is the radial direction. E theta cap is your tangential direction, just like your I cap and J cap. We have talked about a bit about this in polar coordinates. So if I try to apply this formula and differentiate here, I will get the field at point P. First differentiate with R, and you will get 2kp cos theta by R cube er cap, kp sin theta by R cube e theta cap. There, the derivation is not really that important. The results are more important. No one will ask you the derivation generally everywhere. These are the two main results you should know. If I give you a dipole, you should know how to find the potential at a point and field at a point. So let me show it to you. To put this thing. So you can note down this part, what I'm writing now. So if you have a dipole P bar, at this point, the field here will be, so this is the radial direction away from the center, 2kp cos theta by R cube er cap. Now, what is the tangential direction? E is nothing, just like ij cap, you just write e theta er cap. Or if that is confusing, you can simply write it as r cap and write it as theta cap. It is just a denotation, like radial direction in this thing. And what about this direction here? Now, how do you take tangential? See, tangential, you can go this way also, or you can get that way also, right? We always go in the direction of theta. Theta always goes from plus to minus charge. This is important. So rotation goes from plus q to minus q. So this guy will be kp sine theta by r cube e theta cap. There. So at that point, these are the two fields here. So this is called a radial field. And er cap is the denotation for that radial direction. This is your tangential field. So potential at point P will be kp cos theta by r square. Field is this. If you want to find the magnitude of the field, you can square them and add them because both are perpendicular. You end up with kp by r cube root over 2 cos theta square plus sin theta square. There, that is the magnitude of a field at a point. You can also write this in a vector form. EP bar is given by k by r cube into 3 times p bar dot r cap into r cap minus p bar. This is a vector form. If you give me p bar and r bar, I can use this to find the direction. I'll show you how this comes roughly. Like I said, again, not that important. The main results are important here. This is the vector form. You can note down this stuff, especially this field ka part and the potential part. This much is sufficient. Note it now. So in this, the two important cases are, if you take theta is equal to 0 degree, then the point P will be on the line. This is called axial line. And the field here will be simply 2kp by r cube. There will be no tangential component. This will be a straightforward mains law equation. If theta is 90 degrees, this is called equatorial line. So if this is a dipole, so on the perpendicular line somewhere here the field will be parallel to the dipole, and it is kp by r cube. This is the equatorial line. So some two standard results. So there was one question in mains like this. There is a point on the equatorial line and there's a point on the axial line. If their magnitude of fields is same, find the ratio of the distances between them. So you just have to equate this one and this one, like 2 kp1 r1 cube is equal to kp by r2 cube. And they're just asking r1 by r2. I mean, that was a direct question in the exam. Clear, everyone? Yeah, they do similar to the magnets. All these results that you're seeing and deriving, right? We will do the same thing again for bar magnets. You get the same results. There, plus q becomes north pole, minus q becomes south pole. Idea is the same. Clear this? Now, if you look at this guy, look at this, the vector form. What did we do exactly here? So this is your p bar. This is your r bar, and this is your angle theta. So I can resolve p bar into components like this. So this is p cos theta. This is p sin theta. Right? And p cos theta is nothing but p bar dot r cap. Right? And p sin theta, which is the perpendicular component, is nothing but p bar minus p bar dot r cap. Isn't it? So basically, this is your p parallel. Basically, this is your p perpendicular. And we know p bar vector is nothing but p parallel vector plus p perpendicular vector. So p perpendicular will be nothing but p bar minus p parallel, which is p bar. That is the direction of r cap there. This is your p parallel. This will be p bar minus p parallel. I'll just leave it like that. And then what we do? Yeah, we are done. So then what is the net field at that point? I can write this thing as, again, like I said, this is not that important. So p cos theta becomes 2kp parallel r cap by r cube. And this guy becomes, because it is opposite to r bar, this guy will become k by r cube minus p perpendicular. Just add them vectorially. And when you do that, you'll get this result. So now the field at that point will be 2kp parallel, the 2k parallel by r cube minus kp perpendicular by r cube. If you just remove k by r cube, we will get 2 parallel, which is 2 times p bar minus p perpendicular will be again minus p plus p parallel. That is why you are getting 3. You'll get k by r cube. 3 p parallel will be 3 p bar dot r cap into r cap minus p bar. That is the derivation. We got it in terms of vectors. Quite useful. If someone gives you some random directions, p bar is 2y minus 3j 4k, 3-dimensional. And they'll say r bar is some I minus jk. Normally, you can't see and tell who is radial and who is everything. This, in that case, right, will be quite useful. Clear what we did? Just all vector resolutions. So this is p sine theta, but this is opposite to that. That's why we got a minus sign here. Remember the result. That's important. There. Any doubts on this? Let's see some questions on this. So there's the second part of the dipole. how to find the field and potential due to a small dipole. And you guys try this thing. So let's say we have a plus q charge and we have a minus q charge, and let's say the distance between them is 2 mm. We have a point here which is 3 comma root 3. Root 3 comma 3. This is in meters. So that is in millimeters. So dipole is very small. Find the field and potential at this point. Find the field and potential at A. Now, some people will say, sir, why don't I just use regular Coulomb's law and finish it off? Yeah, you can do that, but look at the distances. These are too small. So finding that, then that's when the whole story comes again. So the biggest clue in the questions is this: equal and opposite charges, small distance between them, and the point you want to find is very far. That is a clue, boss. This is a dipole. Get this? Four q by root 3. Okay. Try. I'll give you a minute more. See, if I know p ka value, if I know theta ka value, if I know r ka value, my job is done. I get everything. Let's see. So this will be the dipole here, p bar. So P will be Q. Okay, I should have given you the value for Q, but okay, Q into 2 mm, that is Q into 10 power minus 3. I got P from here. So from here to here, this will be your R, which is root over root 3 square plus 3 square, that is root 12 to root 3. What is the angle? This is where people go for. Which angle should you take? You should take angle from plus to minus. So this angle should be taken. That is theta. Are you getting it? Not the horizontal one. How much will that be? So the opposite side is root 3 and this is 3. So this theta is 30 degrees, not 60. That's what I said. Be clear what is theta. Theta is the angle from the positive to negative charge. There, you got this. Once you're done, then the field will be Kp cos theta by r square. You know everything there. And the field will be this point. This will be the radial field, which is 2 Kp cos theta by r cube, and the tangential field will be which way? Now be careful again. Look at the angle, how it is rotating. It is rotating from plus to minus this direction clockwise. So this field will be this way. Kp sine theta by r cube. Then you can resolve that in terms of I cap, j cap and solve. So that E theta, or the tangential component, it rotates in the direction of theta, and theta rotates from plus to minus. So in this case, it is clockwise. It's not in that other direction. Have a look at this. Clear, everyone? Next thing. Similar one, you try this. What if I give you a charge like this? This is plus q, which is root 2 minus root 2. Let's say this is minus q, which is minus root 2 root 2. And let's say we have point A here. So let's say this is in millimeters, or let's say centimeters. We have a point here which is 3,4. This is in meters. Same thing. Find the field and potential at point A. Just get me the angles and the distances. Hmm. There. So this is how the dipole will look. That's your p bar. And what is this distance? 2 root 2 square, 2 root 2 square, that is 8. This is 4 centimeters. So this will be q into 4 centimeters. This is 5 meters. Remember, theta is measured from positive to negative. So this is the theta we are talking about. This angle is tan 37 is 4 by 3. That is 53 degrees. And this guy is 45 degrees. So theta will be how much? 98 degrees, isn't it? Tan theta is measured like what? That is 45 and that is 53. No? Tan theta 4 by 3 is how much? 53. There. And you got everything. Substitute and you're done. So the field directions will be, this is the E radial. E tangential will be this way. You know the formulas. Clear with this? So the theta is the angle between this one and this one. So this angle we are talking about. R bar is a vector from the center to that point. So this is your R bar. Clear with this? Next thing. So let's say we have a dipole here at the origin. So find the locus of points. So due to this dipole, there is a field everywhere. Find the locus of the points where the electric field is along y-axis. So the field should be only in the y direction. There should be no horizontal component. So if you join all those points, what are the shape that you get? How do you do this? See, here's the point x comma y at some angle theta. So at this point, this field will be 2 kp cos theta by r cube. This field will be kp sine theta by r cube. If that is theta, this will be theta, and this will be 90 minus theta. So you're saying, yeah, tan theta will be plus or minus root 2. There is no vertical component, meaning horizontal components will cancel out. since E bar is along y-axis. Horizontal components cancel out. So we get 2p cos theta by r cube. Cos theta will be kp sine theta by r cube. Sine theta. You get tan square theta is equal to 2. Tan theta will be plus or minus root 2. Tan theta is nothing but y by x. It is actually a straight line. There are two straight lines. So if you draw a straight line passing through the origin like this, two lines, on all these points on this line, the field will be in the vertical direction. There will be an x component. This is clear, everyone. Check it out. Clear, everyone? Next thing. So that is the second part of it. So if I give you a dipole, how to find the field and potential. Next thing. How does a dipole behave in a uniform electric field? So if you take a dipole, P bar, and let's say this is your field D bar, and let's say this angle is theta. So this is nothing but plus q minus q with a distance like this. So this angle is theta. So if you drop and this distance will be how much? This guy will be d by 2. This guy will be d by 2. And this force will be q into e. The field will be in the direction, force will be in the direction of the field. This guy will be QE, opposite to the field. And this perpendicular distance will be d by 2 sine theta. So basically this is forming a couple. We have two equal and opposite forces with a distance between them. So the torque due to this couple will be Q into E d by 2 sine theta into 2 times because there are two of them. So we get torque is equal to Q into D into E into sine theta. And we know Q into D is nothing but dipole. This becomes torque bar is equal to P cross E. So if you put a dipole in a uniform field, the torque that will exert is P cross E. Check it out. Theta is the angle between P bar and D bar. But you know how they'll frame this question? For small angles, now we know torque is equal to Pe sine theta. This is equal to minus I alpha. So I can write this thing as alpha is equal to minus Pe by I into sine theta. For small theta, your alpha becomes equal to minus Pe by I theta. This is your SHM. Therefore, this thing will start oscillating 2 pi root over I by Pe. There, they can ask questions like this also based on dipole. So if you put this dipole and disturb it slightly, it will oscillate with this time period for small angles. There, your SHM doesn't leave anything. Clear, everyone? Now, if there's a torque and a force, there'll be also energy involved. So see, if it's this thing, dipole, this is z bar and this is theta, the work done by external force will be integral torque d theta. Just like F into ds, you can also write torque into d theta. This will be Pe sine theta d theta. Limits will go from theta 1 to theta 2. Sine integral will be minus cos theta, so that will be minus Pe cos theta 2 minus cos theta 1. So if you rotate this dipole slowly by d theta, so basically if you try to rotate this dipole slowly, you have to put some work. So all that work will be nothing but change in potential energy. So we get u of theta 2 minus u of theta 1. And we always choose, we have to choose a reference of potential energy. So we choose 90 degrees as reference. There, so your formula becomes the potential energy as function of theta is minus Pe cos theta. This is nothing but minus P bar dot E bar. There. So your torque is a cross product, your energy is a dot product. So if you look at the cases here, if you have taken E bar like this, they're perpendicular. So theta is 90. So this is your reference line. The potential energy is 0, torque is maximum. If P bar and E bar are parallel, potential energy is minimum, torque is 0. This is a stable equilibrium. If you disturb this, this will oscillate in SHM. If you put P and E in the opposite directions, theta is 180, the potential energy is maximum plus PE, torque is 0, but this is an unstable equilibrium, little disturbance, and this will completely rotate. There, have a look at this picture. So you have stable, unstable, and the 90 degrees is nothing. Clear area. Any doubts on this? So let me ask a simple question like this. Let's say we have a field E bar. We have the dipole P bar. Angle between them is 60 degrees. So this is the main question. Find work done by external force to rotate the dipole 30 degrees towards the electric field. What is the answer? Yeah. What is work done by external force? So when you rotate by 30 degrees, your P bar becomes like this. This angle becomes 30. So work done by external force is U final minus U initial. So U final is minus PE cos 30 minus of minus PE cos 60. Substitute there and you're done. Clear, everyone. Next one. Let's see a theoretical question. So a dipole is placed in presence of a point charge. Remember, if you put a point charge, the field is not uniform. The magnitude is changing, the direction also changes. So we have a point charge Q, right? And you just took a dipole. You kept it however you want. You can keep it like this. You can keep it like this, right? You can keep it like this. It doesn't matter. You can choose whatever direction you want. So the question is, which of the following are possible? You can keep however you want, and then which of the following are possible? Torque on the dipole is 0. Force on the dipole is 0. Torque is 0. Force is not 0. Torque is not 0. Force is 0. Torque is not 0. Force is not 0. You took a dipole and kept it in a, what do you call it, in presence of a point charge. Which of the following four options are true? Which of them can happen? Let's see. First thing, see, if you look at the field lines, the field lines are radial. Now ask yourself, how can I get torque 0? No, I know the formula is not exactly, torque is equal to P cross E. We derived this for E constant. But you can notice something there. if P bar becomes parallel to E bar, then the torque is 0. That means if you can take the dipole and put it along the field lines like this, you'll get torque 0, isn't it? Because both the forces will be along the line. I agree, magnitudes are not same. So this point of force will be something more, let's say F plus dF. This point of force will be F, but they're on the same line, so there'll be no torque. You're getting it? So if you look at this point here, torque is 0, but force is not 0. And if I just show that thing again, if you take a dipole here at this point, the field will be E plus dE. Here the field will be E. So you have forces in the opposite direction, but they're not equal in magnitude. So they won't cancel out. But torque is 0. So there I can find a point where torque is 0. Obviously, I can find a point where torque is also not 0. What about the force? Now for force, again, see, I'll tell you two ways. One thing, to get a 0 force, you need to have opposite directions and equal magnitudes, agreed? The only place you get opposite directions is if you keep it along the field line. But if you get along the field line, the magnitudes are not same. If you try to keep it magnitude same like this, then the forces will be like this and like this. So the forces won't be in the opposite direction. You're getting what is happening? If you keep both the charges equidistant from the charge, you will get equal electric field magnitude, but directions will be different. You cannot get both at the same time. But there is a better way to argue. Tell me one thing. Let's ask the question the reverse way. Due to the dipole, let's find the force on the charge. Listen to this thing. Due to the dipole, let's find the force on the charge. By Newton's third law, this force also will be the same force acting on the dipole due to the charge. Do you agree? Force on dipole due to the charge is equal to force on charge due to dipole. By Newton's third law. Now, if you're saying the force is 0, that means when you keep a dipole, somewhere there is a null point, isn't it? If you keep the charge at the null point, you'll get force 0. Does the dipole have a null point? Does a dipole have a null point? Check out the formula. You'll not get a null point anywhere. No matter what values you substitute here, you'll not get a 0 anywhere. Except at infinity. Sure, infinity doesn't exist. Is that making sense? So there is no null point for a dipole. Meaning you can check like this also. See na, plus q minus q. Tell me where will the null point be? It can't be in the middle. It can't be here because q is closer to minus q. It can't be here. Minus q is closer than plus q. There is no chance you can get a null point anywhere. So we can argue that way. A dipole does not have a null point. That is the point where the field is 0. Therefore, force on the charge can never be 0. And by Newton's third law, the force on the dipole also can never be 0. You can get torque 0, but you can never get 0 force. By third law, the force on dipole is also not 0. So in your options, wherever there is force 0, those are wrong. So these two are right. Is that clear, everyone? You cannot create a 0 force situation. Any doubts on this? Clear? There. That is how it is. Take a break. Come back by 7 and we'll continue from here. If torque is 0, then see, for torque to be 0, P and E can be parallel also, na, abhi tak. ठीक है, take a break, come back in 10 minutes. Yeah, cams on everyone. Let's continue. Next thing. Dipole-dipole interactions. So this is the thing. All that we did is for this part. These things can be asked as questions, theory, everything is same. So case one, let's say if we keep dipole here, P1 bar, and let's say when we keep one more dipole here, P2 bar, and let's say the distance between them is R. And the R is very, very large. Compared to the size of the dipoles. Find the force between them and find the potential energy of the system and the force between them. Find the force and the potential energy of the system. Let's get this try for 2 minutes, and I'll show you how to do one. Think. How do you approach this thing? Others, do keep your cams on. Let's see how to do this thing. So there are 1 or 2 ways to do this. So first one, let me show you a little brute force thing, and then we'll go ahead. Now the thing is, I cannot find the force on dipole directly. So what I'm going to do, this dipole which is there, let's say this is minus q and this is plus q and this distance is d. So P2 is q into d. So I don't know q, I don't know d, but I know q into d is this. So from here to here, so one way is this. So due to this dipole at this point, let the field be E. And let the field be here E plus dE. So E bar is the field due to P1 at minus q. And d is the change in field due to that small distance. Let's call this thing dr. So let's say from here to here, you're changing a distance dr. This is Q into dr. Clear? So then what is the force on the dipole? So force will be minus Q into E, opposite to that, plus Q into E plus dE. And remember, what is the value of the field? The field, this is on an axial line. The formula was 2 kp cos theta by r cube, and theta is 0. So this guy was 2 kp by r cube. So this force will be Q into dE, multiply and divide by dr. So Q into dr, dE by dr. So this will dE by dr will become minus 6 kp by r power 4. And Q into dr becomes P1 bar. So that will be P2, 6 k P1 by r power 4 with a minus sign. So there, minus 6 k P1 P2 by r power 4. That is the force between these two dipoles, everyone. Minus indicates they attract each other. This is one way to do. Take E, D, and do it. In case you didn't like this, right? You can do like this also. Listen, this is a little crude, but it works. P1 bar. So this which is there, this is minus Q, this is plus Q. So from the center till the center, let this distance be R, which is given. Then this distance will be D by 2, and this distance will be D by 2. So I can find the field directly here. So the field here will be 2 kp by r cube. So it will be r minus d by 2 whole cube. Here the field will be 2 kp by r plus d by 2 whole cube. Therefore, the force will be 2 kp minus q, this is p1, by r minus d by 2 whole cube plus 2 kp 2q, 2 kp 1q r plus d by 2 whole cube. So you're saying the distances are r plus 2 and r minus 2. Add them up. Take out 2 kp 1q common. Denominator will become r square minus d square by 4 ka cube. And then if you cross multiply, how much will that be? Actually, you can use binomial approximation. Take out minus 2 kp1q by r cube common. Then do binomial approximation. So this guy will be 1 by 1 plus d by 2r whole cube minus 1 by 1 minus d by 2r whole cube. So if it goes up, you will get 2 kp1q by r cube. This will be 1 minus 3d by 2r, 1 plus 3d by 2r. Same stuff. So this guy will be 2 k p1 q into d by r power 4 into 3. This will be minus 6k p1 p2 by r power 4. In this case, differentiation kuch nahi hai. This is also a way to do. This is a little easier. You're getting what we did? So end of the day, see, the moment you say binomial approximation, you're talking for a very small things, and that is as good as differentiation. So you see whichever method you like. This is something I prefer. But yeah, this thing is more of a brute force. Clear, everyone? There is another way to do this thing. So you still want to find energy, isn't it? So P1 bar. So take it as minus Q plus Q. Same story. Let this point have potential V, and let this point be potential V plus dV. So the potential energy of the system will be minus q into v plus q into v plus dv. So here also you can do that r minus d by 2 r plus d by 2 ka story. This guy will be kp1 by r cube. dv by dr will be minus 3 kp1 by r power 4. So potential energy system will be q into dv. I can write this thing as q into dr, dv by dr. So I'll get potential energy is equal to, that guy will be P2 minus 3k P1 by R power 4. This is R square actually. Kp1 by R square, right? This was a mistake. This is minus 2kp1 by R cube. Therefore, we get the potential energy minus 2k P1 P2 by R cubed. This is the potential energy. And you can get something even faster. What is force? Minus du by dr, remember? If you differentiate this, you will get minus 6k P1 P2 by R power 4. Actually, you can get force and potential energy with one step here only. So if you actually start with potential energy, your life becomes easy. Get potential energy, differentiate, you get field. But just to show you, you can also find force like this by taking field, or like this, or like this. There are three ways you can do this. 189 here, have a look at this. Clear, everyone? Quite a useful results. So remember this. This is for dipoles, P1 bar and P2 bar parallel to each other. Case 2. What if you have a dipole like this P1 bar and we have a dipole like this P2 bar? Both are perpendicular. Now find the force and the potential energy of the system. These are perpendicular dipoles. let's say. Same story, but you will see something interesting. The potential energy is what? Do you get the potential energy part? Now, first thing, see, ask yourself, which one should I take? Should I consider P1 or should I consider P2? The problem with this is, listen, if I take P1 as a dipole and if I take this as plus Q and minus Q, can you see these are at an angles, isn't it? That becomes tough. But if I take P2 as a dipole, and if I take this guy as plus Q and minus Q, can you see this is on the equatorial line for P2? That makes your life easy. So choosing P2 as this thing and this thing as dq, this is dr, this will make your life easy there. So the first part, the potential energy. So potential on the equatorial line is what? Kp cos theta by r square. Theta is 90 degrees, is 0. Therefore, potential energy of the system is 0. So this system has no potential energy. But unfortunately, we can't differentiate this. I didn't get the force. So how do we get the force part? We have to use the other method now. So on the equatorial line, the fields will be here, that the field be E. Remember, equatorial line, the field is opposite to the dipole. Here, the field will be E plus dE. So the field E is given by Kp sine theta by r cube. Theta is 90 here. So this guy becomes Kp by r cube, the tangential component. So dE by dr will be minus 3 Kp 2 by r power 4. So we use this method to get the force. You can't differentiate the potential energy part. It is always 0 there. So this thing will be force. So if you differentiate the du by dr, you get a radial force. So this is a tangential force. How much is this? So this will be q into E minus q into E plus d. So minus q into d minus q into dr and dE by dr. Q into dr becomes P1. So this guy becomes 3k P1 P2 by r power 4. There. So when the dipoles are parallel, you get 6 and here you'll get 3. Clear, everyone? Easy, everyone? Case 3, what if we have dipoles like this? P1 bar and P2 bar. Now what? Yeah, if you remember the results, that will help. If we integrate the value of alpha 4, the potential will be 0. See, the thing is, when you calculated the force, when you said du by dr, you're getting force along the radial direction, right? So in that direction, there's no force. So that's why there's no work. But the force was this direction. There is a perpendicular force. Look at this force, how it was. The force between them was acting perpendicular to each other, isn't it? Can you see this thing? See, in this case, how is the force? The force was along the dipoles. Here, the force is not along the dipoles. That way. Now, listen to this thing. So this is slightly different. So we can do like this. We use a different method here. So if you take any one dipole here, plus q and minus q here, what is the potential energy? The potential energy is minus p bar dot e bar. So I will take P2 and then I'll take the field due to this guy. This is P1 bar. This is P2 bar. So due to this guy, the field will be in this direction, E1 bar. So the potential energy will be minus P2 bar dot E1 bar. Both are opposite. So that guy becomes minus P2 E1 cos 180. So potential energy of the system will be, that is a tangential field. So that is Kp1 by r cube. That straightforward. That's how you get the potential energy. प्लस हो जाएगा k p1 p2 by r cube. Force will be minus du by dr. We'll get a 3 minus of minus will become 3 k p1 p2 by r power 4. This is another way to do this. You find the potential energy using p dot e and then differentiate it, you will get it. So these are the three cases. So do remember the results. I think in 2017 or 16, some year, I was teaching this in a class on Sunday. That day after an advanced exam was going on, and this question came as a paragraph, matrix matching. And the best thing about these results, right? You have rarely seen these kind of results with power 4, isn't it? Do you remember till now how many times you saw power 4? First time you saw in Poiseuille's equation, pi delta p r power 4 by 8 eta L. Then you saw in Stephen's law. This is not r power 4 in the numerator, but denominator. So power 4s are pretty rare. Is this clear, everyone? Check it out. So that is how you do for the dipoles. Clear? There. So with that, we are done with the electrostatics part. So in dipole, primarily we had four things. What is a dipole? How to find for point charges and continuous distribution. Second thing, dipole ka field and potential. Third thing, dipole in a uniform electric field. Fourth thing, dipole-dipole interactions. So the dipole-dipole interactions are important because if you see your chemistry, everything that you talk about, hydrogen bonding, that is all are dipole-dipoles only. So after this electrostatics, right, there is a continuation of this, something called Gauss law and all that stuff that we will do after gravitation. Because like I said, electrostatics and gravitation, they're completely related. So almost 80% chapter matches. In gravitation, we don't have dipoles. In electrostatics, we don't have satellites. So gravitation won't take much of our time. We will finish off that and then we'll come back again to Gauss law. That is the second part of the electrostatics. Because if we do that and then we go to gravitation, there's a good chance you'll start mixing up. Matlab, the formulas you will forget by then. Because now it is fresh, you can easily relate to the stuff. Let's see, we will do at least the intro part today and next class we'll continue on this thing. Universal law of gravitation. So you will see, unlike electrostatics, right? If you remember electrostatics, we had a lot of introduction. What is a charge, properties of charge, then how charge is created on different systems and all that stuff, right? Like here we don't have anything like that because we don't have any conduction, we don't have any induction, we don't have any of those concepts, isn't it? If you make two masses touch each other, masses won't transfer. There is no concept of positive mass and negative mass. If you take a body and put a mass in front of it, it does not induce masses. There's nothing like that, right? Doesn't even make sense. So all these concepts just go off. That's what I'm saying. It makes your life more easy here. So what I noticed, right? If you learn gravitation first and then do electrostatics, you have to repeat each and everything. You have to relearn everything. So it doesn't save you any time. But the people who do electro first and then who do gravitation, I noticed for them it feels like, okay, makes sense. So that thing happens. So that is the reason I always prefer to teach electro first. Yeah, but again, every teacher has his own preference. So what this thing says, every body in the universe attracts every other body with a force proportional to product of the masses. and inversely proportional to the square of the distance between them. Same thing. So if you have masses m1 and if you have masses m2, they will attract each other. So this is the force on 1 due to 2, and this is the force on 2 due to 1. F12 must be equal to minus of F21. The forces are equal and opposite. The magnitude is given by F is equal to minus G m1 m2 by r square. You can see the resemblance. This thing looks like K q1 q2 by r square. The minus sign indicates attraction. So that is one thing. There is no concept of repulsion in gravitation. They'll always attract. So in all the formulas that you studied, there'll be always one minus sign. G is the gravitational constant. Whose value is 6.67 into 10 power minus 11. Negative sign indicates attraction. If you put three masses, all the three masses attract each other. And the force is independent of medium. So there is no concept of dielectric constant epsilon r, वो सब कुछ नहीं है. You put these two masses in a water, you put them in vacuum, you put them in air, the forces are same. The gravitation force does not depend on what medium you present. And that also makes sense. If you remember, why the hell did the force change in the first place? When you kept charges in the medium, they induced charges, and those induced charges messed up the force, isn't it? But in gravitation, there's no concept of induced mass. So that thing doesn't matter only. So force is independent of medium. And we don't have any concept of conduction, induction. You don't induce masses, you don't, the masses don't get transferred from one place to another automatically. All that stuff, nothing works. So you can see the relation there. So Q looks like M, right? K looks like G, right? So what we can do here, 1 by 4 pi epsilon looks like G. So wherever you see 1 by epsilon, you can replace this with 1 by 4 pi G. So 1 by epsilon can be replaced with 4 pi G. Then there you get all the formulas in gravitation. So in every formula that you derived, just replace 1 by epsilon with 4 pi capital G and you got your formulas. We will see that. We will write down all those formulas anyways again. But there, for now, this is the only result that we have. If you have two masses, this is the force between them. Is that clear, everyone? Let's see a question. This is a question and a concept. Let's say we have two stars, mass m1 and mass m2. This is called a binary star system. Our Earth is a single star system. So binary star, there are two stars revolving around each other. Quite an important concept. Means may normally they ask a lot. Two stars of mass m1 and m2, the distance d between them revolve about each other. Due to their gravitational force of attraction. Find the time period for one oscillation or one revolution. So how do they revolve around each other? So this is how it would. Can you hear us?
Our planet Earth, the third of 8 planets in our solar system. Single sun. During the day, the stars. Strange with two. It's almost
Yes,
impossible
how it
to
looks.
observe a binary system of stars with the naked eye, because the stars are usually very close together and appear to be shining from just a single point. In fact,
this is how they rotate.
80% of all stars are members of multiple star systems containing 2 or more.
You're getting how they're rotating? Think of like this, in school, did you play with your friend? You and your friend catches, both of the hands and both of them rotate around each other. It kind of looks like that. For example, if you see, right, Earth and Moon, if you take these two as a system, we are a binary planet system or whatever you want to call it.
More stars.
This is how they rotate.
The way binary systems are formed isn't completely known. We simply can't live long enough to see. However, the most likely way for a binary star system to form, dense nebula.
So that's how it
Gravity
looks.
starts to pull the gas inwards and collapses it in.
How do we do this thing? So if you see, right, most of the stars that you see, almost 8 to 10% stars are binary stars. So what he was saying, you can't see them because the light is so bright, you think it is a single point. In Andhra, right, when people get married, there is a custom. After the marriage gets over, they take the couple outside and they show them a star in the sky. It is called Arundhati Nakshatram. Right? So in this thing, right, in whatever, in our history or mythology or whatever it is, Arundhati, right, is the name of a sages. So there was a sage and his wife ka name is Arundhati. So she was a very powerful lady and all that stuff. So those two stars, right, so are a binary star. So they're actually two stars revolving around each other. So what they try to do is, after the marriage gets over, they show the couple the two stars as a symbolic representation. Like, this, so the way the two stars are together forever, you also be like that. So that was the thing. So when my sister got married, right, this guy took us out and he was showing in the sky, and I was looking there and there's nothing there. I said, what are you trying to show exactly? So, and then the priest explained this to me and I said, but there's nothing there. I said, yeah, it will be there. Don't worry about it. And the best part is this, when I got married, they took me out and they showed in the sky and there's a building there. I said, building to dekh raha hai. He said, roughly it will be there. Just, put namaskar and come off. Don't, try to argue and all that shit. So, but the thing is that means, if you see, we knew about this concept called binary stars some hundreds of years back. But if you look at the history of astronomy, right, binary stars were first discovered in somewhere 1920s or 30s. So that way, so we did have knowledge, but somewhere down the line we just wasted it. So how do we approach this problem? But again, simple story. Both the stars are moving, but someone else is not moving. The center of mass. Since there is no external force on the system, that's how we start the problem. Since F external is 0, center of mass is at rest. So therefore, stars rotate about the center of mass. So okay, that was the main concept in the question. So if I draw the picture, this is how it looks. So this is M1. This is M2. If you take this as the center of mass, or I can take this is the center of mass. So after some time, this is what will happen. So this guy is going in this circle. This guy is going in a bigger circle. Both are going in two different circles. So after some time, M1 will come here. M2 will be here. Getting this? And they will divide in the ratio of R1 is to R2. And how do you get R1 and R2? So R1 will be, they will be in the opposite ratio, M2 d by M1 plus M2. R2 will be m1d by m1 plus m2. So the centromast divides them in the opposite ratio masses. Now if you draw FBD of any one of them, I will draw FBD for m2. The force of attraction between them will be gm1 m2 by d square. It will depend on the total distance between them. But the centrifugal force m omega square, it will depend only on the radius of the circle, which is m2 omega square r2. Are you getting the difference? The attraction force is due to the distance between the planets. The centrifugal force m omega square r is the radius. And then you're done. Since both are this thing, you'll get gm1 m2 by d square. This is m2 omega square. R2 will be m1 d by m1 plus m2. M1 m2 goes off. We will get omega is equal to root over g m1 plus m2 by d cube. This is your angular velocity. Therefore, time period will be 2 pi by omega. You could have taken the other planet, you would have got the same answer. Because both of them have same omega. Is this clear, everyone? Any doubts on this? So this is a binary star, two stars revolving around each other. Why? What happens if you have big velocity? What is the problem?
No, sir. Like, if they don't have velocity, then they will crash into each other, right, directly.
So they should have some velocity, right? Obviously.
So, sir, is there any like minimum velocity required, or is it just any amount of velocity?
If you have different velocities, you'll have different omegas. So the distance is given, this is fixed, right? This number can't change. It depends on the distance between them.
Okay.
Now same one, now you guys try similar one. Let's say instead of a 2-star system, you have a 6-star system. Again, completely hypothetical. They don't exist. You don't even find a 3-star systems. These are very unstable. M, 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 and M. So all the 6 stars are revolving around each other. It's a regular hexagon A. Find the time period for one revolution. Six stars rotate about their common center of mass. So just to give an idea how to do this, you find the force due to this, 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 and this, isn't it? 5 forces. All these 5 forces must be equal to the centrifugal force. That is the idea, isn't it? If there are 6, the remaining 5 are attracting this one guy, and that force is becoming equal to the centrifugal force. Try. I'll give you a minute or two. The numbers are bad. Let's see. So for simplicity, right, let me write F is equal to G m square by a square. Okay. So this guy will attract with a force of F. Remember the distance between these 2 points? √3. That will be √3a. So this force will be how much? G m square by √3a square F by 3. From here to here, the distance is 2a. So this force will be F by 4. This also will be F by 3. This will be F. So these are the forces here. And all these are balanced by the centrifugal force m omega square a. You can clearly see here, this is the symmetry point line. And what are the angles here? This guy will be 30. This guy will be 30. Agreed? And these angles will be 60 and this angle will be 60. Sure? So what is the resultant force? 2F cos 60 plus 2F by 3 cos 30 plus F by 4. This is the net force acting on that one particle on the hexagon. This is equal to m omega square a. यहाँ से omega आ गया. Time period will be 2 pi by omega. Check your forces. Is that clear, everyone? And if you want, I can show you the angles again. Say, so there are two forces like this, F and F. This was the resultant. This was 60 and this was 60. And then we had two forces like this, F by 3 and F by 3. And this thing was 30 and 30. And then we had one F by 4 in that direction. So yeah, let's start them up. All vectors, right? Other than the fact G m1 m2 by r square, everything else becomes something. Just find the net force and finish off with circular motion. Is this clear, everyone? So there, so questions will be like this only. You will find the questions quite similar to electrostatics, but there are different types. But the thing is, you can't find a problem like this in electrostatics. Can you tell me why? Because if I put 6 charges, all will repel away, right? You can't make all of them attract everyone. You're getting my point, what I'm saying? You can't make every mass attract every other mass. Chalo, if I put all plus plus plus, kya hoga? All will repel away. If they repel, they'll fly to infinity, na? They won't go in on orbit. You're getting it? Suppose if I say, okay, sir, I'll do one thing. I'll put plus q, plus q, plus q, I'll put minus q. Chalo, isko attract karoge, but this will get repelled away, na? You can never create a stable system. You can't get this kind of questions in electrostatics. Is that making sense? Because here all forces are attractive. Electron, if you put like charges, all will repel. Clear with this? So there are some models there. So we'll continue from here on Tuesday when we catch up on Tuesday at 5:30 as usual. We'll continue with gravitation. We will see all the formulas. I will write on every formula that we derived in electrostatics in gravitation form. Then we'll do more variations of these problems, especially gravitation based. Okay, with that we'll wrap up for the day, right? And this week our test is online till Sunday 11 o'clock, and the portion in that, right, you don't have dipole, but you have everything else. So you can give that. It's an easy mains level paper, so do give it a try. Okay, with that we'll wrap up for the day, right? So I'll see you guys again next week. And remember, next week, right, we are on a break for